Of a myocyte, the original image was a bit dark. So just by linear stretching 0.2 to 0.6 to 0.0 to 1. So this is on a normalized scale of 0 to 1. You can achieve some enhancement of the contrast and brightness, but if you look at the histogram, this is the original histogram, and after stretching, you have many unoccupied levels in the histogram. So you're not still making full use of the information available in the sense the histogram is limited to this range. There is a little bit of stretching here, but many levels are unoccupied. So that's not the best enhancement, but it is a poor image to begin with. These are linear transforms, except for the first one, thresholding, that is nonlinear. Stretching, like I have shown, is linear. There could be clipping at the ends, but within the transform portion shown, it is linear. I showed this HD curve earlier for an imaging system. It can also be used for enhancement. This is a curve that shows in a certain range I want to cut values, and below this value I want everything to be 0. And above that value, some value, I can saturate, I don't care. In between, I want good enhancement, stretching, like this, or more stretching. So this is known as gamma of the imaging system. That's the response of the system. If you know that for the system you acquired, from which you acquired the image, you can correct for that. If you want a linear response, you are going to invert it. But if you are using this idea for enhancement, you are not concerned with what happened during image acquisition, the gamma of the image acquisition system, but you're simply saying, I'm going to use a nonlinear transformation with this gamma function. A system with a large gamma has image with high contrast, as I mentioned earlier. It may not utilize the full range of the available gray scale. Small gamma, image with wide latitude but poor contrast, wide dynamic range. Gamma correction is a nonlinear transformation that says GMN, the output is FMN times gamma, FMN to the power of gamma. Now for this, the grayscale is normalized to the range 0 to 1. Divide by the maximum and then apply this. There is another definition where you can take the log of FMN, you're not normalizing, it could be 0 to 255 if you wish, divide by gamma, and that's also gamma correction. You can also incorporate grayscale windowing and say below some level I don't want, let the output be 0, above some level let it be maximum, and in between apply gamma and nonlinear transformation. So here we have a chest X-ray image, gamma equal to 0.3, gamma equal to 2.0. So different details are enhanced. Soft tissue details come out better. Hard tissue details are saturated. Hard tissue details are there, and soft tissue, here it is enhanced a bit, but this part is lost. So it is selective enhancement. So by getting multiple images of this nature, you concentrate on certain regions and design suitable enhancement parameters for those regions. If you want to examine the other regions, you take apply another gamma value, get a different output image. So if you don't do any transformation, linear is that is gamma equal to 0.3. So there is enhancement here, but after that there is not much enhancement. Here there is more enhancement on the lower side. What is 0 to 0.3? Sorry, it is compressed here. 0 to 0.3 is compressed to 0 to 0.1. So some parts are compressed, some parts are enhanced, stretched, depending on the value of gamma being greater than 1 or less than 1. Now, histogram-based techniques were popular. There are some limitations, but there are some interesting aspects. So we'll quickly go through a few histogram-based techniques. The image histogram is normalized and interpreted as a PDF, as a probability density function. You only have one image, so you take its histogram, divide by the total number of pixels, and call that a PDF. So based upon information theory, the information conveyed by the image is maximal when the PDF is uniform. But we are taking the PDF of one image, so it's only approximate. And the idea of a flat histogram conveying maximal information is based on information theory using probabilities that may not always apply to real life images. So there are limitations. The entropy of the PDF is maximum when it is uniform. So the technique of histogram equalization is proposed as a method to enhance the appearance of an image based upon these principles. Will that work? We will see. So you have an image FMN and you have the histogram PFL. Divide by the number of pixels and let PFR be the normalized histogram. Let R be 1 over L minus 1 so that the grayscale is in the range 0 to 1. You're normalizing the counts of the pixels as well as the pixel values. Then you have a probability density function PFR. F is the input image, R is the input variable. And if you apply some transformation, S equal to TR, then the output is given by PGS. G is the output image, P is the probability density function, S is the output variable. The input PFR times the derivative of dr over ds at R equal to T inverse S. Then the resulting image GMN will have normalized gray levels in the range 0 to S. S being between 0 and 1. The input is also in that range. So S equal to TR, and you want to design it so that the output histogram is flat. So the derivation of this is in the book by Papoulis that we use as a textbook for random variables. It's also in the book by Gonzalez and Wentz. The transformation you want is integral of the PDF of the input image. W is some temporary variable, integrate it. So if you integrate the probability density function, you get the cumulative distribution function. Some call it probability distribution function. So this TR now has these important properties. It is single valued and it is monotonically increasing because you are adding probability values that cannot be negative in the interval 0 to 1 for R. This is necessary to maintain black to white transition. When you apply a transform like this, you cannot go backward and reduce the output gray level when the input is increasing. So you want monotonically increasing functions for the transform. And this transform output is between 0 and 1 for the input being between 0 and 1. It maintains the same range of the variable R and S, input and output variables. Now the derivative of this transformation is PFR. The derivative of the integral is just that function. So we said earlier PGS is PFR times its derivative of the transform, and that is 1 over this, so it is equal to 1. So regardless of what the input PDF is, the output PDF is 1 due to this transformation. So all you do is integrate or apply a cumulative summation procedure to the input histogram, and that itself is a transformation. And because they're all normalized, the values are all between 0 and 1 for the variable and also the probability. So TR equalizes the histogram of the given image. The histogram or the PDF of the output image is flat or uniform, and that has maximal entropy. The histogram has maximal entropy. Will the image have maximum quality? That varies. In the case of a discrete image with discrete gray levels, then there are a few issues. Implementation in practice. The derivation was with continuous variables. Now when you have discrete variables, you have an image FMN, P equal to MN pixels and L gray levels, so they are quantized. Divide by the maximum, so RK, the quantized pixel values are between 0 and 1, but then there are only L of them, L values, each occurring NK times. So the PDF may be approximated by the histogram NK over P. Number of times each pixel occurs divided by the total number of pixels, that's all. The integration SK equal to TRK, the transformation is sum I going 0 to K PFRI. The interval becomes a sum of all the probabilities of occurrence of the input gray levels, which is sum I going 0 to K of Ni over P. Ni is the number of times the ith gray level occurs in the input. Discrete. So this is the transformation. Output is Sk. Sum of these values which are all between 0 and 1. And that sum could be something different from these Rk quantized levels, which are 0, 1 over 255, 2 over 255, and so on. And these values are something else. So you need to map these values back to one of those input levels. That is where some approximation comes in. Take the nearest available level, and then there are some undesired effects. Discrete histogram transformation may yield values of Sk, will yield values of Sk that may not equal the available quantized values for display. You have to multiply that by 255. The values will have to be re-quantized, and hence the output image may only have an approximately uniform image, but in a uniform histogram, but it is not. Typically, it is far from that. So the resulting values in the range 0 to 1, you scale to 0 to 255 for display. That's not a problem. Regardless, the quantized levels are remapped, and many of those values of Sk may go to the same output value. So histogram equalization is typically implemented as a lookup table. LUT is lookup table, Sk-Rk pairs. You prepare that and apply as a lookup table. As long as the PDF is the same, you use the same. So if you have a population of images with an averaged histogram taken and an average PDF, then that's fine. You're not computing the PDF from one image. Then the same lookup table could be applied for that whole category of images. So the problem is this: a quantized histogram equalizing transformation may contain several many to one gray level mappings. Many input levels will go to the same output level. So it is not reversible. Reversing is not important, but many of them going to the same value will cause some artifacts. So the transformation is non-unique and irreversible, but that is not the main issue. Sometimes it works. So this is a girl in a snow cave. One of the daughters of my grad student, William Morrow. So she is sitting inside the snow cave. Even kids play in snow. It could be minus 30, but even if it is minus 30, kids have to go out and play in outside when there is a recess in the school. And they have camps where they go in the winter, and they build snow caves. And you can build an igloo. Not you, I wouldn't do that, but my son has done that. In scout camps, they go and they build an igloo, and they have to make sure it is strong enough, stamp it and make a hole, and they sleep and spend the night there. I don't know why they do that, but they do. So then you want to take a picture. There is a lot of white snow on the outside reflecting light, and she is inside and there is not much light there. Your camera takes the average light intensity, and that's the original picture. And this is histogram equalization. Not bad, you can see her, but it's a little blurry. That's not a problem, but better than that, right? In terms of visibility of what is inside. And this is linear mapping, 0 to 23 mapped to 0 to 255. I took only this range, and if that disturbs me, excuse me, I can't. Thank you. But everything outside is saturated. So if you want only that part of the image, you can do a linear transformation, or you can do a gamma correction, 0.3 gamma. So this is not bad. There are variations there, which you can see. There are variations inside that are retained. Is this better or that? It's up to you. There are no rules here as to say which is better. Look at the histogram. This is the histogram of the original image, and this is the histogram after 411B is histogram equalization. Not bad. The histogram has been spread. It's not equal, but flatter than that. You want a flat histogram? Is this flat? No. Is this flat? A little bit. But many levels are not occupied. Zero probability. Clearly, this is a multimodal histogram. That is the histogram equalizing transformation, or the lookup table. There are these steps. So all of these input levels will map to that output level. So many levels don't exist in the output, which is why you see these holes or gaps. So the X-ray image and chest X-ray and histogram equalization. The transformation is sort of almost linear. There is not much gain in here. There is not much improvement, and this looks almost like a straight line. That's the histogram of the output. The original histogram, I think we saw somewhere else. In 4.6 somewhere. We don't need to go back. Here it completely ruined the image. This is that myocyte image. Histogram equalization has enhanced all these details which we are not interested in. The histogram equalization almost looks like a step function. There was a big spike and then the histogram went low. So suddenly the values increased when integrated, and then flat, and here flat. So all of these have been either saturated or clipped. That's the output histogram. It's not uniform. It's not just a histogram being uniform. There are other structural details and structural information one needs to look into to judge whether the result is good or not. In textbooks, there is another method called histogram specification, where you can say, well, the uniform histogram may not always help, may not give a good image. I'll specify what the histogram should be for the output. How I'll do that, that's a different question. How do I know what kind of histogram will lead to a better image? If you have some information about that, then you could draw or specify that histogram, and then say, let the output have that kind of a histogram. For that, you have to put in series two histogram equalizing procedures. Histogram equalization can only give one output image. Take it or leave it, as we saw. In many cases, you will leave it. The user has no control over the procedure or the result. So if you want to have a choice, then you say, I will specify the output histogram. And we have a series of histogram equalization steps that will give you an output that is close to the pre-specified histogram. May not be exactly the same. And if you can specify several histograms, how you do that, again, I don't know. Somehow you do that with some experience, and you can get several enhanced images, and then you can choose one of them. So suppose PDT is the desired, D is desired, T is the variable for that histogram, is what you specify. The input image F has PFR as its PDF. We earlier saw S equal to T1R, integral of PF, will give you histogram equalization. So this is one step of histogram equalization from the input end. So this gives you a flat histogram, theoretically. Now you do another histogram equalization from the other end. To do histogram equalization, you only need the PDF, PD. You don't need the image. The transformation is computed by integrating the PDF or the histogram. You can draw a histogram without having an image. So integrate that and have this Q equal to T2T as an equalizing transform applied to your desired histogram for which you don't have an image. Now both of these will give you a flat histogram. Then you'll say, well, that histogram is the same, it's a flat histogram. Let me connect the other two histograms through one transformation. So let the hypothetical image so obtained be E with gray levels Q, and T equal to T2 inverse Q will map the gray levels Q back to T. Now this PGS and PEQ are both uniform PDFs and they're identical. So the desired PDF may be obtained by applying T2 inverse to S. You have two transforms, T1R and T2, but now T2 inverse applied to S. We assume that T2 inverse exists, and that is a problem if there are many to one transformations, if there are those steps in between, and they exist. It is not a single valued or unique transform, but we will assume that is possible or approximate. So in practice, you cannot do the inverse, but you match the two lookup tables and try to put them together. There's one lookup table for the forward equalization transform from the given image. There is one lookup for the reverse histogram equalization from the desired histogram, and make lookup tables for the two and somehow connect those values and make one transformation from input to output. So specify the desired histogram PDT. Derive the histogram equalization transform Q equal to T2T. Derive the histogram equalizing transform S equal to T1R from the input image, PFR. Apply the inverse transform T2 to the PDF obtained in that step, T equal to T2 inverse S, and then T equal to T2 inverse T1R. Combine T2 inverse and T1 apply to the input gray level R, and that is the full specification transform. Apply that to the input image F, and that gives the desired result D with the specified or an approximation to the specified histogram. Many of my students did projects on this and implemented various algorithms with interface and so on, but we never got any result worth displaying. You can draw whatever histogram you want, and I don't have any result to show. Textbooks Gonzalez and Woods may have some, but I didn't find any particular advantage any further than equalization. It is something fun to try perhaps, but it hasn't led to any great applications. But theoretically there is some interesting procedure here.
But one probability distribution to another distribution, desired distribution.
Yeah. And it works in the continuous case with the assumption that these are, at least one of them is reversible or invertible. But in a practical case with quantized gray levels and many to one transforms in both T1 and T2, there are approximations. And you further approximate by making one lookup table. So if you want, you can try, but there is nothing great about it. I still keep it as an interesting topic. You may take some of these ideas and put them elsewhere. Now these are global operations, the histogram operations. So they don't take into account the non-stationary nature of images, one histogram or PDF for the whole image, like one spectrum for the whole image. So you want to have local and adaptive transforms for effective enhancement. That leads to what is called local area histogram equalization. This has been popular more than specification of histograms. There are many variants of this LAHE, L-A-H-E, local area histogram equalization, contrast limited, CLAHE, and various AHE, and so on. So Ketchum came up with this procedure and said the histogram of the pixels within a 2D sliding rectangular window. So for the pixel being processed, you put a window and compute the histogram there and equalize that and apply the result only there for that one pixel, move and keep repeating. That's expensive. So the result is applied to only one pixel. It's repeated for every pixel. The window provides a local context. That's fine, it is adaptive. So Peiser came up with many variations of this. The histogram equalizing transforms are computed not for every pixel, but there is some interpolation. I'll divide the image into some blocks. I'll compute only a few histograms. And for other pixels in between, you interpolate between those histograms or those outputs. So some approximation to reduce computation. So it is not computed for every pixel, but only for a number of non-overlapping or in some cases overlapping blocks. And for other pixels for which you don't have the transform, you use the neighboring transforms, take their average and put the value there. So the pixels at the center of each block are processed using the corresponding transform. Other pixels get interpolated versions of the transform corresponding to the 4 neighbors, which have the transforms. And then they applied some limits on contrast enhancement, said, within a small window, you don't want to stretch to the full range of the image. Then white becomes black, black becomes white, and so on. You don't want that. Within a small window, here, if you stretch to the maximum 0 to 255, that will become black, this will become full white, 255, you don't want that. So you want to have the local range and limit your stretching to that range as you move the window. So here are a few versions. So this is the girl in the snow cave. This is global histogram equalization I showed earlier. This is locally adaptive histogram with 11 by 11 window, a 101 by 101 window. And these are not very good because there was no limit on the contrast. We didn't implement the contrast limited version of this. That would have given better results. We have that in the new book. We are working on it. We have some better results with contrast limited adaptive histogram equalization. We were more interested at that time with our version of the adaptive neighborhood. So we said we will use the adaptive neighborhood computed for each pixel, take the neighborhood, the ribbon also into account, take that histogram, do the equalization, apply that result to the pixel at the seed pixel and also the redundant seed pixels. So we got these two with different parameters, growth tolerance 16, background 5 pixels, growth tolerance 64, and background width 8 pixels, where if you use a large window, growth tolerance being 64, you get larger windows. This reversal is not good. Snow is not black. So that relatively dark region of snow has become black. You don't want that. It's a little better here. But a funny thing happens here with the enhancement of this edge of the cave. It looks like she has been pulled to the front. Depth information is lost. There you know she is at the back. Here it, yeah, maybe, but looks like she has come to the front. So you lose some depth information when some cues are lost. The 3D perception cues are lost in this process. But you can see some details. There is that string here, which you cannot see there, but could see there, but you can clearly see here. The patterns on the boots are hard to see there. So there is enhancement. If you look at minor details. So in adaptive neighborhood histogram equalization, we use these adaptive neighborhoods. I think I can skip the details. I already said that. So here is another example, a test image. There is a box here. Inside that there is another box, and there is another box inside. Same here. If you do global histogram equalization, you can see one box there, which you cannot see here. This box, maybe you can see, you cannot see here, but there's one more inside you cannot see. That becomes a bit more visible here. If you drag the window, adaptive histogram equalization window, then the artifacts of the window will come. With our adaptive neighborhood, you don't see such artifacts. And if you were to adjust the lighting conditions and concentrate, you will be able to see another little square inside. which is not visible there. So test images like this will help in analyzing what can be achieved and what kind of artifacts could possibly arise. And we can make this to be just about the just noticeable difference and see what happens, and adjust the contrast enhancement parameters so that details that are at a certain level above noise are enhanced and those at the noise level are not enhanced. It depends on what you want to do. You don't want to enhance noise. There are a number of 3x3 convolution mask operators. We have already seen the 3x3 mean filter. We saw the Laplacian. But there are a number of other 3x3 convolutions that are popular through textbooks and in practical applications. They have been proposed for various types of image enhancement and edge extraction. An old technique that is popular, that was popular and is perhaps still popular, is unsharp masking. It's an awkward name. When an image is blurred by some unknown phenomenon, you could assume that each pixel in the original image somehow spread and gave its part of its value to its neighbors, like diffusing. You don't have an exact equation for diffusion, it is some spreading. So it spread, it had some value, it lost some value here and gave some value to the neighbors. So this, and it is additive. These values were added to the neighbors. A certain fraction of its value went away. Then each pixel is composed of its own value and fractional components of its immediate neighbors. The spreading of the value of a pixel into its neighbors may be viewed as local fog or blurred background. You could also model it as diffusion, but that's an entirely different procedure, and we are putting that in our second edition. I don't have it here. Diffusion-based image processing is another technique. There was a photographic technique that was popular when film was used and paper printing or printing on film was used. So in the photographic lab, what was done was, if you had a blurry image, then the given degraded image in its negative form was further blurred to create what would have been the background fog. And a positive transparency is created. You make that, invert that and make it positive on film. And the original negative and the positive created after blurring are put together, and then you make a print. But you must register them properly. If the edges are registered, then it's okay. The procedure leads to subtraction because one is positive, the other is negative. This blurred fog is subtracted out. So what the pixel gained from its neighbors in the process of image acquisition is now removed. So that was called unsharp masking. And a convolution mask to do that is this, which says, from this value, I'm subtracting an average of its 8 neighbors. But if I say 1 in the middle and minus 1/8 all the way around, the net is 0, and it's a differentiation. But I want to retain the intensity, so you make this 2. But you can change this if you want and adjust the weighting between retention of the original value and the derivative. If I make this 1, it is like a derivative, like a Laplacian. My central value minus the average of the neighbors. It's a local derivative. Plus 1, the current pixel. So the original image plus its derivative of some kind is what is happening here. So it's a convolution mask. You apply it on a pixel by pixel basis. There is no need to reverse. It's symmetric. The net sum of these coefficients is 1, so the intensity is maintained, average intensity. You can also write it in this format, as we had seen in some of the filtering techniques. There is a combination between the input signal, GMN, and a high-pass version, GMN minus mu G. Signal minus mean is like a high-pass filter, plus alpha. Previously we had the mean here, with alpha being some ratio of standard deviations or variances. So here it is the original image. Original image plus its derivative with some controlling factor. If you make alpha equal to 1, you get that 3 by 3 mask. So there is a local gradient. This is a local gradient or derivative. So that is related to edges. And adding that edge information will give you edge enhancement. But this creates edge enhancement. It leads to high frequency and emphasis, but edges are enhanced. Do you want edges highlighted or not? Radiologists don't like edge enhancement. It's like highlighting. Strong edges will have clearly perceptible overshoot and undershoot. That's a problem. You have forward derivatives and backward derivatives, and that causes some artifacts. I'll show that later on. It could lead to negative pixel values in the enhanced image because there is a derivative taken. You're adding that with a weight factor, but still there could be negative values. What do you want to do with that? You want to set them to 0, or do you take the minimum to maximum and map to 0 to 255? It's up to you as to how you want to display the result. So here is that clock image. It's noisy by itself and unsharp masking. A little sharper. Some of these details are a little sharper. A little more noisy perhaps. We'll come to this later on. So this myocyte, there is not much enhancement, a little bit enhancement. This one, perhaps there is good enhancement here. We'll come back to this later. The knee, there is not much of an enhancement. This is already fairly good. Now this is one of our shapes image. It already has sharp edges, but I still wanted to apply this method and show the artifact that comes. You see a black line around the edges. This is the original object. This is after enhancement. The edge, white, black. You don't see it everywhere. These are not very strong edges, but at strong edges you see that more obviously. You can see that there too. You may not be able to catch that on this full image with so many details, but it is there. The subtracting Laplacian is something similar, but it has some basis. There is a diffusion basis based on this partial differential equation. So it says the observed image G is a function of time. There is an image, the original image was there, and over time it is diffused. The intensity is somehow diffusing. It is spreading over space. Like you put ink on a blotting paper. I said blotting paper, and many of my students didn't know what blotting paper is or was. All of you know what blotting paper is?
Tissue paper.
No, not tissue paper. No, some of them don't know what. It's ancient technology. Blotting paper is thick, loose cellulose paper on which if you put liquid, if you put ink, it spreads. It was used to absorb ink. In olden days when you used ink pen or fountain pen, if you were to write, it would take time for the ink to dry, so you would use a roller with paper that could absorb that excess ink. It was called blotting paper. You would take the excess out. That paper absorbs the liquid, like your paper towel that absorbs water and so on. So that was called blotting paper, and nobody uses that apparently nowadays. But if you were to try to write something on blotting paper, you write something, it keeps spreading because the paper absorbs and it keeps diffusing. So if you were to put a picture on such a medium, it keeps spreading. And that is blurring. You draw a straight line, but it spreads. So like that, the image is changing over time, but spreading and getting blurrier due to diffusion. It could be heat that spreads. If there is a some conductive substance. It could be liquid that is spreading. It could be what else that spreads. Imagine some situations. And that spreading process is indicated as the derivative of the function g, the image over time, is kappa nabla square g, where the nabla square is the Laplacian. It's a spatial derivative. The temporal derivative is equal to the spatial derivative with a scale factor. That's the model for a partial differential equation for diffusion. It's a linear process here. There are some other nonlinear models. So at t equal to 0, we assume that gxy0, this is time 0, is fxy, the original image. We don't have that. We took the picture sometime later. It's become blurry. So at t equal to tau greater than 0, the degraded image gxy tau is observed. And if you were to expand that in Taylor series, gxy tau is gxy0 plus tau partial derivative xy tau, tau square over 2, second partial derivative xy tau, and so on. Ignore the rest, use only these. Then this is f. So you take the original is this minus that. But this derivative is nabla square, the Laplacian. This is also thrown out. So the enhanced image is g minus k tau nabla square g, the Laplacian. So from the given image, you subtract a fraction or some weighted factor of the Laplacian of the image. The enhanced image is a weighted subtraction of the given image and its gradient, which is the Laplacian in this case, according to this model. So there is a model. The unsharp masking also had a conceptual model, but no mathematical model. Here we have a mathematical model, and that leads to the Laplacian we saw is this in discrete notation. This is the Laplacian, the gradient. The sum of these coefficients is 0. Subtracting Laplacian, 1 minus that. So 1 minus minus 4 becomes 5, and around 1 you have 0, so these become minus 1. So that's the subtracting Laplacian. 5 minus 1 for the 4 connected neighbors. The 8 connected neighbors, the corners are not used. It's similar to unsharp masking. This minus the average of its neighbors. If you want, you can divide by 5 or 4, and if you divide by 4, you get the average of that, and this is 5 over 4, which is 1 plus 1 over 4. So you can see it in different ways. The other one was 2 and minus 1 over 8. The sum of this is 1. So there is a similarity. Unsharp masking is sometimes called generalized Laplacian. And this is also a kind of unsharp masking. The Laplacian doesn't maintain intensity information. It shows only edges of gradient. Subtracting Laplacian maintains intensity and provides a sharper image, enhancement. It again leads to negative pixels. You have to deal with that. But what happens with negative values is the input was 0 to 255. The output could be minus 200 to plus 400 or something. So the larger dynamic range. Now you have to display it to 0 to 255 for the output. So you compress that. So the enhancement you gained is lost by compression if you keep the negative values. So there are some practical issues and difficulties as to how to handle this. If you just chop off all the negative values, many parts will be set to 0, and that doesn't work. So mapping of this to the output is an issue. It also introduces disturbing overshoot and undershoot, like we saw earlier, and that can be visualized by this 1D signal. This is a rectangle pulse. Derivative will have those delta functions ideally, but here I'm showing like that. And when you take the second derivative, you get that. When you subtract the 2, you get this. So undershoot, overshoot, overshoot, undershoot. That is what is showing in the image of those black and white, brighter and darker lines. So this illustrates what is happening. Even if this edge is, of course, the edge won't be like that, it will be smooth. The derivative of that could be a Gaussian. And the derivative of that will certainly have positive and negative values, and that will lead to this problem. So this is the Laplacian, subtracting Laplacian. Because you're using the second derivative, noise is emphasized. In general, the subtracting Laplacian gives you more noisy image. It is sharp. 6, look at the 6 or 5. You can see the 5 clearly, better than those. But a lot of noise that's present in the image, it's been enhanced. The gradient shows the noise too. Laplacian, subtracting Laplacian. This is not bad. Better than that. I will just click through these and you may decide. Some of these, I don't know what they are. They look better than in the original. And the ringing artifact is clear. The gradient shows that. So fixed operators have certain limitations. Fixed meaning not varying over space. Subtracting Laplacian and unsharp masking, mean, median, they do the same thing all over the image. The coefficients and size of such filters don't vary. The filters cannot adapt to changes in the nature of the image from one location to another. So operators with fixed coefficients and fixed spatial scope cannot take non-stationarity and multi-scale features into account. Multi-scale meaning small objects and big objects. As in my test patterns, and even in the clock image, there is a big minute arm, a small hour arm, and then all these numerals. So there are objects of different, details of different scale. Multi-scale features cannot be taken into account because the mask is of the same size. The same thing is done all over. So we need adaptive filters. You said 4:30, right, today? Close early? Let me see where I am. Just a moment. Where am I? Okay, not far from the end, but I won't go to the end. High frequency emphasis is a frequency domain technique where you want to emphasize the high frequency components that are related to edges and sharpness. So you boost high frequency, control the low frequency. You can't remove them completely. You cannot remove DC. You need the brightness, but you boost certain components. High frequency components in the Fourier transform could be boosted. And it follows from the effect of differentiation we saw. When you differentiate an image, there is increasing gain for high frequency components. So the ideal high pass filter, like the low pass we saw, says HUV is 1 if DUV is greater than D naught, some cutoff, 0 otherwise. So this is a high pass filter. Everything below that cutoff is set to 0. DUV is square root of U square plus V square, distance from the origin or radial frequency. That simply extracts edges. The magnitude transfer function is this 0 inside this disk or circle, 1 outside. That is the Butterworth. Well, there is a smooth transition. So ideal goes 0 to 1. Butterworth goes slowly. If you take the Butterworth and apply a bias and raise the DC gain so it is not 0 but goes to here 0.5 and above, then it's a high frequency emphasis filter retaining the low frequency. More gain for high frequency than for low frequency. So the Butterworth high pass filter says similar to the low pass, just this is reversed, this ratio, D0 over DUV. For low pass it was DUV over D0. That's all. So this is a monotonic function in the passband and stop band, like what you see here, monotonically increasing. Positive frequency, negative frequency in one section, radial section. N is the order of the filter. If you increase it, it will be a sharper transition. If the DC gain is 0, then intensity information is removed. That's a high pass filter. So you get only the edges. And again, the results will have positive and negative values. You have to deal with that in displaying. If enhancement is desired, then you have to maintain intensity information, and then you can use a Butterworth high emphasis filter. All it does is it puts a bias, raises the filter, a constant, and if you want to control the maximum value, you put another factor there. If you want the maximum to be 1, then you divide by the max and normalize that. But DC gain is not 0. The rest is the same. So a few examples. The clock image again. Ideal high-pass filter will introduce ringing artifacts. Butterworth high-pass filter, and this is the Butterworth high-emphasis filter. So there is some sharpening here without ringing artifact. That's not good. This is not good for enhancement. Here intensity information is maintained. This area is bright, that area is dark. Here that brightness variation is removed by the high-pass filter. This is that myocyte image. This is quite good actually. High frequency emphasis has sharpened some details. The ringing artifact has ruined this. Output of the ideal high pass. Here too, ringing artifact. I should also say there is ringing artifact from the edges because I zero padded. Some of these are non-square images. So for FFT and to apply the Butterworth filter, I couldn't do that with some non-square image. I could possibly do that, but making it a square image helps in the frequency domain. With the Butterworth high emphasis, these details are enhanced. We don't need that. This image doesn't need enhancement. Okay, 4:28. You want to stop here? If I start this, it will take more time. There is just a little bit left in this chapter. We will close this tomorrow and then move on to, what is next? Segmentation, is it? Next is segmentation, or detection of objects. So tomorrow we will just finish this and move on to the next topic.